Welcome back to BE 110 Continuum Mechanics. Today we're going to consider the kinematics of a moving material region R0 in the reference state of the body B0 that moves and changes shape to become R in the current state of the body B. As before, we'll consider a point in the reference state with position vector capital X. But now we'll also consider a point that's a small distance, delta big X away, and we'll imagine what happens to this vector as the material moves and deforms so that delta big X in the reference state becomes delta little x in the current state of the body. So the reference coordinates are components of the position vector capital X. And the Lagrangian or material description of this motion is little x equals little x of big X and t. The current or deformed coordinates are the components xi of the position vector little x. The Eulerian or spatial description of this motion will be big X equals big X of little x and t. So now we can consider the transformation that takes delta big X to delta little x. Since delta big X and delta little x are vectors, then the transformation that turns delta big X into delta little x must be a tensor, and that tensor is F. F is known as the deformation gradient tensor. It's a rank 2 tensor, it's non-singular, and in general it's not symmetric. Now, in the limit, as delta big X tends to 0, we can use the chain rule to relate the components of delta little xi to delta big Xr by the partial derivative del xi del xr. Therefore, the components of the deformation gradient tensor, F, I, R, are the partial derivatives of the deformed or current coordinates del little xr with respect to the undeformed or reference coordinates del big Xr.
Let's try an example now. Given the Lagrangian description of the displacement field u in a body as the following: u1 equals alpha times x1 plus beta times big X2, u2 equals gamma times big X2, and u3 equals delta times big X3, where big X1, 2, and 3 are the original reference coordinates. What are the components of the deformation gradient tensor F? Are they A? F has components alpha, beta, 0, beta, gamma, 0, 0, 0, delta. Or B, F has components alpha plus 1, beta, 0, 0, gamma plus 1, 0, 0, 0, delta plus 1. Or C, F has components alpha plus 1, beta plus 1, 0, 0, gamma plus 1, 0, 0, 0, delta. Or D, F has components alpha plus 1, beta, 0, beta, gamma plus 1, 0, 0, and delta plus 1. Or E, none of the above. Okay, let's try and work it out. Well, u1 is x1 minus big X1, which means that little x1 is equal to alpha times big X1 plus big X1 plus beta times big X2, or alpha plus 1 times big X1 plus beta times big X2. So that's a Lagrangian description for the deformed coordinates. U2 is little x2 minus big X2, so little x2, the deformed coordinate, is gamma big X2 plus big X2, or gamma plus 1 times big X2. U3 is little x3 minus big X3, so the deformed x3 is equal to delta times big X3 plus big X3, or delta plus 1 times big X3. So now taking partial derivatives of each of these functions, little x1, 2, and 3 with respect to big x1, 2, and 3, we get del little x1 del big x1 equals alpha plus 1, del little x1 del big x2 equals beta, del little x1 del big x3 equals 0. This is the first row of the deformation gradient tensor. Del little x2 del big x1 is 0, del little x2 del big x2 is gamma plus 1, del little x2 del big x3 is 0. Del little x3 del big x1 is 0. Its derivative with respect to big x2 is 0, and its derivative with respect to big x3 is delta plus 1. So these are the components of the deformation gradient tensor, which you'll see appear in answer B. So B is the correct answer.